Let's get started. So what have we been trying to do? So we yeah. Yeah. Well, what makes you think I did not?
Someone texted asking if we start. Have they started?
There are 4 people in Zoom. Yeah.
Okay.
So we are going to look at what we looked at. We looked at quantum statistics of particles. And I want to emphasize here, we were not looking at what is known as quasi-particles. We were looking at real particles. So we had some energy levels, energy level epsilon 1, energy level epsilon 2, energy level epsilon 3, so on and so forth. And we had n particles. So we said that if you have n1 in epsilon 1, n2 in epsilon 2, n3 in epsilon 3, so on and so forth, then total number of particles is going to be summation nj. And the total energy, not quasi-particles, and total energy is going to be summation epsilon j and j. And then we said that for Bose-Einstein, nj can be 0, 1, 2, ... For Fermi-Dirac, nj can be 0 or 1, right? This was the 2 statistics we were interested in. And we could have done this using canonical partition function. We would have written down Q of NVT, and that would have looked like summing over all microstate e to the power minus beta E nu, right? And Chandler describes this. Chandler says you could have tried to do this. How would it have looked like? It would have looked like going to any energy level and looking at the value of the occupation number of that level, which can go from 0 to some larger value, and then doing here e to the power minus beta summation j nj epsilon j. What should be the limit here? What value can nj take in this case? Arman, what do you think? Are you sure? Capital N.
Capital N.
Yeah.
3N.
Capital N in this case, not 3n. That's why I'm doing this once again. So we are talking about n particles, not quasi-particles, n particles, right? And what Bose-Einstein is saying that you don't have any limit. You can pack in 0, 1, 2. It's again, let's think about that bus in India, right? You can keep packing as many as you can. But there is a finite number of people on the planet, right? So you cannot go more than that. That's the point here, right? He's laughing over. And it's a good analogy, I think. So you cannot go more than n. But so we could have done this summation, but there is a problem. In order to do this summation, we also need to impose constraints, right? These things are all connected to each other. We have to impose the constraint that at any particular value of these things, n1 plus n2 plus nj must sum up to capital N, and that n1 epsilon 1 plus n2 epsilon 2 plus nj epsilon j plus ... must sum up to E. In this case, not E, because E will come out there if you are doing a canonical ensemble. So we don't have to worry about this constraint because we are trying to do it in, since we are doing NVT. So E will come out of it. But this is a horrible integral. This is a horrible summation, right? You're not summing independent things. You have everything connected. You cannot do this summation nicely. Why were we able to use canonical partition function when we did the harmonic oscillator? In harmonic oscillator, we had a similar situation. In harmonic oscillator, classical or quantum, we had 3n independent oscillators. So the total number of particles, in a sense, was fixed. But these were independent. So then we went and looked at them one at a time. And when we looked at them one at a time, we again drew a picture like the one above, right? We talked about the energy levels. What was the difference between the energy levels that we talked about for one oscillator versus what we are talking about here? Why were we able to get away with canonical partition function for harmonic oscillator? What made that summation, the similar summation for canonical harmonic oscillator? Why were we able to do that? Did we have the constraints there? We did not have the constraint, right? The phonons could be created as many as you want. So this constraint was not needed. Those of you who came late, that's okay. But if you look at my notes, it won't make sense what I talked about. So please go and watch the video. Today's first 5-10 minutes, definitely watch it, because I think this is a subtle point, which is not obvious to remember, as to why did we suddenly, why were we not able to use canonical partition function for these quantum particles? These are particles, these are not quasi-particles. For phonons, for harmonic oscillators, the phonons are quasi-particles. You can have as many as you want, right? So we did not have this restricting sum over there. That's why we were able to get away with it. And this is why we used a grand canonical partition function for this case. So we said, okay, n is finite, but let it fluctuate, right? That's what we said. We said, let it fluctuate, and it's better to impose a chemical potential on this problem. So that's what we did. So we solved quantum particles. And again, it's not quasi-particles. We were looking at real, whatever it means, real particles, quantum particle statistics by looking at Z mu VT, the grand canonical partition function. And what is Z mu VT going to be? That's going to go to every microstate and sum up e to the power minus beta, E nu minus mu and nu. What is the value of E nu? E nu is again going to be epsilon1 plus epsilon2 plus epsilon3 plus dot dot dot. N nu is going to be n1 epsilon plus n2 epsilon 2 plus n3 epsilon 3 and dot dot dot. And instead of mu, you're actually summing over n1, n2, n3 and all these things, right? So we did all this. And what did we get out of this? The result that we derived last time looked like follows. We calculated the grand canonical partition function for Fermi-Dirac and for both Bose-Einstein. And we could write it down in the following way, in a compact way. It turned out to be product over all J's, all energy levels, 1 plus minus, so plus corresponds to Fermi-Dirac and minus corresponds to Bose-Einstein, e to the power minus beta epsilon j minus mu to the power plus minus 1. This is, we wrote it in a slightly different algebra last time, but it's the same thing. So this is what we got. So it looks complicated, but you know, it came out of the math and it's actually not that complicated. Then the other thing we derived is, what is the average occupation number in a given energy level? In energy level 1, 2, 3, 4, whichever it is, what is the average value? And that came out to be, again, we will write it together for Fermi-Dirac and Bose-Einstein. And I'm going to call this as equation number 1. And this thing came out to be 1 by e to the power beta epsilon j minus mu plus minus 1. So this is all quantum particles. We know what is the, we have imposed a temperature, we have imposed a volume, and we have imposed a chemical potential mu. And we calculated what is the average value of energy level. Are these quantum particles distinguishable or indistinguishable? Huh? Indistinguishable? Why? What do you think? They are saying that's quantum. That's the nature of quantum. So these were indistinguishable particles. So what I want to do next is to think about, could I have written down a classical way of thinking to write down the partition function for something like this? And you have seen a relation like that. It showed up. We haven't really talked about it. And when I grade your midterm this weekend, I'm not going to take into account any error due to this correction, in fact, error correction, because today is the first time we are really going to talk about this. So what I want to do, what?
In equation 1, I don't think you should have a plus minus 1 in the exponent. It should just be minus 1.
I think I should.
In the power, because it's 1 over 1 plus minus for the product, if I'm not mistaken. For the
okay, well, you can check here. Yeah. Let me see. One moment. It's possible. So check this. We are not going to use that. What we are going to use is the second equation. So I'm not too concerned. I don't have my notes from last time. So, but yeah, check whether you should have a plus minus 1 there or not. The second one is definitely correct. Let's focus on that one. So what I want to do now is to next, we are going to show what happens to quantum particles statistics, so both Bose-Einstein and Fermi-Dirac, as temperature is increased and as the density goes to 0. We will see that in this limit, we recover classical behavior. What does classical behavior mean? If you were to think about classical indistinguishable n particles, how would you attack the problem? Which partition function would you use? Canonical or grand canonical? In volume V and temperature T. Canonical, right? Because I've told you N, V, and T. Yeah, N is kept constant, right? So, okay, canonical. How would I proceed next? Let's say that the partition function for one particle is Q1, which I have to calculate, right? The difficulty is always in calculating Q1. If you're assuming independent systems, the combined partition function is a product or something like that. But then you have to go and do all the jugglery in getting Q1, right? That's why we had to assume the energy eigenvalues and things like that. So if we had Q1, and I want you to think about the total Q of the system, what will be the relation between Q and Q1? Huh? Power? Anything else?
Divide by n factorial.
Divide by n factorial. Why? Because that's what counting makes us think, right? If it's just really counting, we should be able to do this, right? So is this equation really valid? So I could write it down one step further, that it would look like, let me reduce the size of my handwriting, so I write one more equation. So this is going to be 1 by n factorial. So let me write it down as Q is equal to 1 over n factorial. And for each particle, I can go to the energy levels and count them, right? And calculate the partition function and take its power to the n. So this, let's call this equation number 3. So the question I ask for you is, does equation number 1 reduce to equation number 3 in high temperature and low particle density limit? It should. If it did not, then classical mechanics, we know that classical mechanics is the limit of quantum mechanics, right? In very, very high temperature and very, very low density. That's what we would like to show. How does this happen? And you'll see naturally why the 1 n factorial correction actually does come out, but only in that limit, okay? I wanna make one more point. This equation 3 is very interesting. So who here has done ever DFT calculation, density function theory? You have done it. You have also done DFT? Okay, good. And JP, have you not done DFT? Really? Yeah, okay. So DFT is a calculation where people solve for the eigenvalues of a system at 0 temperature. You know, it's a way of solving Schrodinger's equation. Forget about dynamics, just solve it. And what DFT does is to give you values of this epsilon j. It gives you values of the energy level, right? You solve Schrodinger's equation, you find the energy. So this equation shows you that if you could calculate the values of the energy levels at 0 temperature, you could actually write down the partition function. And now you have information about thermodynamics at any temperature of interest, right? This is partly what makes, there is a reason that Walter Kohn was given the Nobel Prize for DFT. You know, people use equations like this, but there is a problem. The problem is, in order to use something like this, you need to know not just the first ground state and the first excited state epsilon j, you need to know all of them, right? You need to do this summation, not just for the first or second energy level. You need to calculate everything, otherwise there will be errors. So this equation is used a lot in chemistry and physics. So, but today what we are going to do is to find a pathway to go from equation number 1 to equation number 3 in high temperature and low density limit, okay? So what do I mean by high temperature and low density limit? So our number of particles is given as summation j nj, right? So if we think about the average number of particles, that's going to be, go to any energy level and calculate the average number of particles in that energy level, right? And here we can use equation 2 that we wrote on the last page, the value of Nj. That's going to be summation j plus minus 1 to the power minus 1. Here I'm pretty sure there is only power minus 1 on the top. And plus is for Fermi-Dirac, minus is for Bose-Einstein. If you forget which is for Fermi-Dirac, which is for Bose-Einstein, you have to remember only Bose-Einstein shows a condensation, right? So the minus sign can happen. The denominator can go to 0 only in Bose-Einstein. That's how you remember that the negative sign happens for Bose-Einstein. Let's call this equation number 4. And we are talking about high temperature and low density. So what is density? Density is average number of particles divided by volume. So today's lecture is going to be a lot of algebra, very simple algebra, intuitive steps, but a lot of algebra. So stay with me, okay? Otherwise you'll be like, what's going on? So at high temperatures, if I now draw let's draw a box. And in this box, let's say this is energy epsilon 1, this is energy epsilon 2, this is energy epsilon 3, this is energy epsilon 4, so on and so forth. I could also draw it vertical, I just put it horizontal, right? And so at high temperatures, and now I want to draw a 1 if there is something in this energy level, epsilon 1, and a 0 if it's empty, okay? 1 if it's full, 0 it's empty. At high temperature, how do you expect this to look like? A very, very high temperature. Let's start with Bose-Einstein. How should this number look like? It should be mostly zeros, right? Every once in a while, you will see a 1 because there are some particles, right? But most of the time, it will look like 0, right? 0, 0, 0, 1, right? How about Fermi-Dirac? Actually, for both, what I meant to say is, well, let's start with Fermi-Dirac. For Fermi-Dirac, you know, it cannot be more than 2 in the same. But for both, there's just so many energy levels, and you have pumped in, the temperature is so high that you don't want to stay in one energy level, right? There's so many. It's like, I don't know what's an analogy to give for it. You know, it's like you have entered a very, 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 very big hotel with rooms on every floor, and there's an elevator that goes up back and forth very, very fast, and you can take any floor. So it's very unlikely that any given floor, even though I could pack up everyone on one floor, the probability that I find everyone on the same floor is really small, right? Because you can very easily get to any floor that you want. So it's high temperature. At high temperature, both Fermi-Dirac and Bose-Einstein have lots of states accessible. That's the physical point I'm trying to make, right? You can just access any state. It's possible that in Bose-Einstein, one of them looks like a 2, right? It's possible that maybe it looks like a 3, but the probability just starts to go down. Because if this one looks like a 3, any thermal fluctuation will quickly take it to the next one, right? That's the point here. So you won't pack it up. You will just have a very, very, very low number of, so what this means now, if I think about, so this is J is equal to 1, this is J is equal to 2, this is J is equal to 3. If I think about the average value of Nj for any J, what is that going to look like at very, very high temperatures? Huh?
Low.
Very low, right? It's going to be much smaller than 1. Because sometimes it can be 1, but almost most of the times it's going to be a 0, right? That's the point. And this is true for both Fermi-Dirac and Bose-Einstein, okay? This is kind of subtle, but keep in mind there's just so many levels that it does not matter. Let's call this equation number 5. So what we have really done here is to say that the number of states, all of this will be true only if the number of states is more than the number of particles. And I'm already giving you a hint for a problem that's going to show up on your next homework. So if you had a system where there were only 2 states, this picture won't work, right? You cannot do that. There is nothing high to be populated. So this already gives you a sense of what I'm going to conclude at the end of the class today, that the n factorial approximation works only if this is true. If the system has lots and lots of states. If it's not lots and lots of states, if it's only a small number of energy levels, this won't work. If you have a finite number of energy levels and if you have very few particles, it still might work. But if you have like 100 particles and you have 100 energy levels, it's not going to work. The number of levels should always be, number of states or levels should always be many more than the number of particles. So that's our starting point. Okay, like I said, there is a lot of algebra and every line on its own is not complicated algebra, but there's intuition as we go from line to line. Okay, so if something is not clear, please interrupt me and ask. So what we have just shown is that Nj in low density and high T, T high, low rho and T high, this is going to be true. Okay, but then we actually wrote down the value of Nj in equation number 2, right? We know what Nj is. Equation 2 said that Nj is e to the power beta epsilon j minus mu plus minus 1 to the power minus 1, or 1 by, and again, I forget. So which one should be Bose-Einstein, lower or minus, upper? Minus, right? So lower one, because you know it has condensation. So Fermi-Dirac Bose-Einstein. So this is plus minus 1. So I am saying that this quantity is much smaller than 1. What does it tell me about the denominator? It must be much bigger than 1, right? That's the only way it's going to happen. In the denominator, there are 2 things. Only one of them can be much bigger than 1. Why? Because the second one is 1 identically. So this means equation 2 plus equation 5 means that what we must have is that e to the power beta epsilon j minus mu must be much bigger than 1. That's the only way this is going to happen for both Fermi-Dirac and Bose-Einstein. As the temperature becomes very high and as the density becomes very low, that's how this is going to happen. So therefore, what can we write down Nj as? Therefore, Nj is going to be approximately, if this thing is more than 1, does it make sense to worry about plus minus 1 on top of it? No, it's like gazillion plus minus 1. Who cares, right? So Nj, average Nj will therefore be e to the power minus beta epsilon j minus mu. Something happened in this equation. We don't have to write anymore Bose-Einstein or Fermi-Dirac. That plus minus was coming from this thing over here, and that just disappeared. So you're already starting to see that how Bose-Einstein and Fermi-Dirac are starting to look kind of similar. We assumed it in our this picture. That is what we assumed. So that's what we are seeing now more mathematically, that as temperature becomes higher and density becomes smaller, the average Nj looks like e to the power beta epsilon j minus mu. Everyone happy with this? And this is true for both Fermi-Dirac and Bose-Einstein. I will write down this equation on the next page. So we just showed that at high T and low density, average Nj for both Fermi-Dirac and Bose-Einstein is approximately e to the power minus beta epsilon j minus mu. So now we can write down the value of n. What was n? Well, we can't connect n to average value of Nj, right? But we can connect the average value of n to the average value of Nj, right? So the average value of n is going to be, and why can't we talk about n? Well, we could. It will be fluctuating, right? We are working in a grand canonical ensemble, right? So we talk about average value of n. That's going to be summation Nj. And now we can use this equation on the top and we write it here. That's going to be j e to the power minus beta epsilon j e to the power plus beta mu. So this becomes e to the power plus beta mu summation e to the power minus beta epsilon j. Or let's take this thing to the left-hand side. Or, well, no, actually, let's take this thing to the left-hand side. So what does that give? That gives us that e to the power beta mu is equal to average n by summation j e to the power minus beta epsilon j. Okay, just one more manipulation and I want to number a few more equations. This equation I'm going to call 5a up here, and this I'm going to call 5b. Okay, so now I can write down my average value of nj a bit cleaner. So average value of nj is what? It is e to the power, average value of j is this thing, right? So it is e to the power beta mu multiplied by e to the power minus beta epsilon g. So we have to take this thing and multiply it with e to the power minus beta epsilon j, right? So what does that become? That becomes average value of n multiplied by e to the power minus beta epsilon j and this I will call equation 5. Have we seen something like equation 5 before in PChem or elsewhere? What's equation 5 telling us? It's the Boltzmann probability. It's telling us that the level of particles, the average number of particles in energy level, in any energy level, is simply proportional to e to the power minus beta epsilon j, right? This is Boltzmann probability. This is the, some people call it the classical Boltzmann factor. Nj is proportional to n, the total number of particles, multiplied by e to the power minus beta epsilon j. Right? This is what we use in chemistry all the time when we think about rates, even organic chemists know it, right? Yeah, go ahead. Yeah. Are you stretching or raising your hand?
No, both.
Okay.
Yeah, no, it's like, yeah. Why didn't we? Again, why you said that the denominator is greater than 1, but why at the same time didn't we account for the fact that beta is close to 0, so that this factor is close to 1. So my point is, can you make it clear, like the approximations that we use?
I think the approximation is okay because we are looking at the total thing. There is no other way. The whole thing, I cannot go and decouple. So it's telling us something about, yeah, I see your point. You're saying if beta is going to 0.
Okay, I can see that this approximation maybe like works if epsilon j is large. Like for the,
yeah, so that is why we are working in. So another way of thinking about it is that don't take this approximation to talk too much about energy levels close to the ground state. This is really true for excited state, which is fine because we are thinking about high temperature, right? That's the idea here. So it's kind of circular, but it's robust. Okay, and we are deriving classical behavior at high temperature, right? So being in the ground state is extremely unlikely. You will be in some excited state. That's the point. But yeah, that's a good point. So this is the Boltzmann probability. We are not quite done yet. We still have to go in order to show what we wanted to show, which is what did we want to show? We wanted to show that this Q, which all of you were able to say, multiply the partition function and divide by n factorial. How does it follow from this expression for Nj that we wrote? Okay, that's what we have to show. So in order to do that, what do we want to do? Okay, I will give a moment, then I will go to the next page. Okay, so our quantum treatment has Z as a function of mu Vt. Our classical treatment has Q as a function of nVt, and we need to reconcile both of these, right? How do we reconcile both of these? Through thermodynamics, okay? So what is the connection of the grand canonical partition function with thermodynamics? We know that beta multiplied by pressure multiplied by volume is equal to log of Z. What is the connection of canonical partition function with thermodynamics? We know that minus beta A is equal to log of Q. And we know there is something that connects A and PV, right? There are thermodynamic relations that might allow us to manipulate that. So we have to do a bit of thermo before we come back to StatMech. So let's think about A. A is going to be E minus TS, right? That's the definition of A, right? Helmholtz free energy. Let's think about G, and it's going to look like a bit like magic. I'm just throwing out thermodynamics out there, but once you look at the notes, again, once you go back home today, please look at it, you'll see why I did it the way I did it. G is going to be E plus PV minus TS, right? That's the definition of G, right? H minus TS. How do we connect G to chemical potential? What is the relation between G, chemical potential, and N? Mu N, good. I'm very happy to see that many of you said that. It always confuses me. Wait, why did it happen? But that's true, right? That was the definition of mu. It is G divided by N. If it was a multi-component system, then it won't be true, right? Then we would have to do mu1 N1 plus mu2 N2 plus mu3 N3. But we are working with simple single component system for now. So let's call this as mu, and we are working in a grand canonical system. So we have to think about average value of N, right? So mu average value of N is going to be average value of energy plus PV minus TS. Okay, let's call this equation number 7. Now multiply everything by beta. So this becomes beta mu average value of N is equal to beta E plus beta PV minus beta TS. Okay. What can we say about beta E minus beta TS? What is E minus TS? A, right? So what is beta E minus beta TS? Beta A. So beta mu average value of N is beta A. This thing in red becomes beta A. And what is beta PV? ln Z. So we just derived a very interesting, basically thermo relation between one more step and then we are there before I claim that we derived something beautiful. So this is beta mu N, and what is beta A? That is minus ln Q plus ln Z. So what have we just shown? We have shown that ln Q is equal to minus beta mu N plus ln Z. So you have a direct relation between the grand canonical partition function and the canonical partition function. Oh, Vedant, are you still there?
Yep.
I'm pretty sure this plus minus 1 that I wrote is correct. I know why you're getting confused, because last time in class, I did another manipulation. I multiplied, divided by something, but that plus minus 1 is correct.
Okay.
I'm going to... Huh?
Down this.
It's correct, and I'm going to use it. If it's not correct, it matters actually. You will see in the following derivation that if we did not have plus minus 1, we would be, Fermi-Dirac and Bose-Einstein would show us differing behavior in the classical limit. So yeah. So, okay, so we have this relation that connects Q with Z. Okay, and now what we have is we calculated Z. That was equation number 1, right? So use equation 1 in equation 8. Equation 1 was the value of Z for both Fermi-Dirac and Bose-Einstein. So let's put that over here and let's plug through it, and it will start to simplify soon. So that gives us ln Q is equal to minus beta mu average value of N plus ln. And what was Z? That was a product over all energy levels. 1 plus minus e to the power minus beta epsilon j minus mu. And I claim that this plus minus 1 is correct. Okay, let's bring that plus minus 1 outside. It's a log of products, right? Log of products raised to the power. So the power can become a prefactor of the log, right? So this plus minus 1 can come outside over here. And then it's going to look like ln q is equal to minus beta mu average value of n plus minus ln product over j 1 plus minus e to the power minus beta epsilon j minus mu. Now we have gotten rid of the plus minus from the power. Okay. It's a ln of product. What can we write a ln of product as? We can write it as sum of ln, right? It will simplify our life. So that I will do on the next page. So we have ln q is equal to minus beta mu n, and we are replacing in this, right, our last expression was the plus minus from the exponent came out up front, and we had ln of product, and we are going to write it as a sum over ln. So this becomes plus minus summation j ln of 1 plus minus e to the power plus beta mu minus epsilon j. Okay. Let's call this equation number 9. What can we do now? We are interested in the high temperature low density limit, right? What is the meaning of that limit? High T low rho limit means Nj is much smaller than 1. And remember last page, no, 2 pages ago, we just showed that Nj, 3 pages ago, we just showed that Nj much smaller than 1 means that e to the power beta epsilon j minus mu is much bigger than 1, right? That's the way it's only going to happen, like overside at higher energy level. So let's not worry too much about that. So e to the power beta epsilon j minus mu must be much more equal, much more bigger than 1. So we said e to the power beta epsilon j minus mu much more than 1. Where did we say that? We said this on bottom of page 4. Bottom of page 4. What do we have in the expression in equation 9? That's not the same thing. That is with a minus sign, right? So if this is much more than 1, then e to the power plus beta mu minus epsilon j is going to be much smaller than 1, right? Now we have something interesting. Inside the summation, we have ln of 1 plus minus x, where x is much smaller than 1. Anyone knows what is this series? Plus minus x. Right? This is very useful if you want to do mental arithmetic. If you want to multiply, Feynman used to be very good at this. He could multiply, he could take cube roots of very complicated things very, very quickly. And he would use basically this formula. If you have to take cube root of something, right, you should write it as a log. And then the cube becomes 1 by 3 multiplied by a log. And if you know how to approximate logs using this formula, that was his trick. If you read his book, I don't know which one he talks about. In Surely You're Joking or What Do You Care Other People Think. One of the book he talks about it, that how he had committed like a bunch of log things to memory. He did not have ChatGPT, right? So, okay. So we can write down ln of 1 plus minus x is approximately plus minus x. So equation 9 now, and this is why I said the plus minus mattered, becomes ln q is approximately minus beta mu average n plus minus summation j. And now this thing becomes plus minus e to the power beta mu minus epsilon j. What happens to the plus minus now? When it's plus, it's a plus. When it's a minus, it's a minus. The net product is just an overall plus. So ln q is now approximately minus beta mu average n plus summation j e to the power beta mu minus epsilon j for both Fermi-Dirac and Bose-Einstein. And this is kind of nice. It happened because we kept that plus minus in the exponent. If we had not done that, as Vedant wanted us to, Vedant would have got us terribly, terribly screwed. So the lesson of this story is don't listen to Vedant. That's okay. You should listen to Vedant. Hey, Vedant, Patrick is staying here. You guys should fight it out. It's none of my business. So we're almost there. We just showed that ln q is equal to this thing. We still don't have our equation for the classical. The 1 over n factorial hasn't showed up. We have to make one more substitution. If all the, I don't want to zoom. If all the equations were up here, you would have seen immediately which one. But basically, we have to use equation number 5b, the expression for e to the power beta mu. Okay, that's why I numbered it. So use this. I am. Oh, actually, before we do that, we can do something even simpler. ln q is therefore approximately minus beta mu n. Does anyone realize what is this thing? Have you seen this before today? That's average n in the high temperature, low particle density limit. Average n is summation j, this thing in that limit, right? That's the whole thing. So what this thing that is dangling over here, this summation is actually nothing but average n. Okay. Here we have used equation 5a. Using, I mean, I promise you it's a lot of algebra. It's simple, but you have to, every equation gets used. That's why I numbered everything. Now we have to use 5b. Okay, and we are almost there to see Stirling's formula in reverse action. 5b says that e to the power beta mu is average n divided by summation j e to the power minus beta epsilon j. Okay. Let's call this equation 11, and I'm going to write it on the next page again for the sake of continuity. So equation 11 said ln q is minus beta mu average n plus average n. This was equation 11. And equation 5a, equation 5b said that e to the power beta mu is average n by summation j e to the power minus beta epsilon j. So we're going to bring back now the summation j once again, but in a different form. So if I take the log of this, both sides, what do I get? The log of left side is beta mu. The log of right side is ln n minus ln summation j e to the power minus beta epsilon j, right? I just took the log of both sides. Let's call this 12. Now put 12 in 11, and we are basically done. I can see in my notes, I go up till only 13. So you can relax. Put 12 in 11. What does that give us? ln q is equal to beta mu multiplied by minus average n, right? So let's use the value of beta mu over here. So this is ln q is equal to minus ln of average n. We have a minus beta mu, right? So minus of ln n, and this becomes a plus ln summation j e to the power minus beta epsilon j multiplied by average n. So we have got rid of the beta mu in the first part of equation 11, okay? Plus average n. Okay. Now I am going to do something that some of you might not like. I'm going to say, well, we are really starting to think about canonical partition function, right? We are switching our viewpoint now. We are really thinking about canonical partition function. So there is no point in dangling this average, the bracket notation with n, right? It's canonical. So this must be a constant. So we are just going to use n over here, okay? Because we have now forgotten about z. All the z business is gone, right? In this equation, there is no z. There is a mu, but there is no z. Actually, mu is also gone, right? You see, mu had to go for z to go away, right? So that's why we removed mu, because we totally wanted to come away from grand canonical to canonical. So mu is gone. So if we use this, what do we get? We get ln q is equal to, this is an n, so that becomes minus n ln n. And this thing becomes plus n, and plus n ln summation j e to the power minus beta epsilon j. Have we seen n minus n ln n before? That's Stirling's approximation, right? So we use it in reverse. So ln q is now approximately minus ln n factorial plus n. I like this derivation a lot, even though it's just a bunch of algebra. It's worth doing it once because you see how it really nicely comes out. Okay, or ln q is approximately ln of this n that is hanging here in the prefactor can now be brought inside and taken to the power, right? So ln of summation j e to the power minus beta epsilon j to the power n divided by n factorial, or ln q, it's ln both sides. Let's get rid of the ln, or q is approximately 1 by n factorial q1 to the power n by n factorial. So we just showed how it came. Okay, so this derivation is something, yeah, you can stare at it. It's just like magic. It comes out nicely. So, no, there is no n factorial extra. We kind of ignored this little n.
Oh, for
No, we did not ignore it. That stayed. Oh, that one. Oh, yeah, sure. I got excited. Sorry. That would be terrible. Okay. That won't be extensive. Yeah, sure. Correct? So this is a relation we could have just written down, but now you see where it's really coming from. And it really happened only at the high temperature, low density, lots and lots of states. So don't use the n factorial approximation blindly. You have to be careful in using it. Only if there are lots and lots of states, you can use it. Otherwise, it's not going to work. So let me summarize then. So any questions about this?
So we're assuming that n's a constant and that.
Because we came to canonical, mu is now disappeared. Okay. And we got this relation. Okay. So I want to summarize the average. So this we showed, but we showed something else today, which I want to summarize now before you get lost in all we did is this derivation. So we showed that Nj Fermi-Dirac is 1 by e to the power beta epsilon j minus mu plus 1. We showed Nj Bose-Einstein is 1 by e to the power beta epsilon j minus mu minus 1. And we showed Nj classical. How much was this one? Boltzmann factor, right? Average number of n multiplied by e to the power minus beta epsilon j divided by summation j e to the power minus beta epsilon j. And by showing that the classical canonical partition function is recovered, we have basically showed the third relation, right? That it's true that these three are equivalent. All three are equivalent, not across all temperatures or densities, in high T and low density. Both are important. If you're at high T and high density, even then that approximation might start to break, right? Because bosons would be like, oh, no, I just want to pack up here, right? And you won't have NJ much smaller than 1. So you really need both of these to happen. So classical mechanics is not just the high temperature limit of quantum mechanics. Classical mechanics is the high temperature and low density limit of classical mechanics. Lots and lots of states, all accessible, very few particles. You have to remember all these three things for classical behavior to emerge from quantum behavior. Okay, so I'm going to stop here today because this is good. So next class, which is Tuesday, before that, you will have your third and fourth homework combined. It's going to be a long one, but I'm pretty sure I have covered all the homework problems. You will be like, oh yeah, this you mentioned. I don't think there is going to be anything new. It will just be filling the dots of maybe one problem could be new, but it won't be like, I don't think any of the problems is going to be a complicated, your friend is getting depressed in grad school, you have to help the friend out type of problem. It will be like just basic problems work through the algebra, but it will be useful. And midterm graded will be available on Tuesday. I will bring it. And next class, we are going to look at the free electron model for metals. And we will look at heat capacity once again and show that for free electrons, the heat capacity at high density. So next time we are going to do something opposite of this. We will show that free electrons at low temperature, so opposite of this, and high density, opposite of this, so like very quantum behavior, the heat capacity is proportional to temperature. We will do that. Then the last topic in non-interacting systems we will do is photons, which will again be similar, just like phonons. It's not good. It's kind of almost amazing as to how similar it is and how you can derive the Stefan Boltzmann law, which is T⁴ law for black body radiation, basically with very similar algebra to what we have done for phonons. It's really like universal. You see the universality so in a nice way. That will be the end of non-interacting systems. Then we'll go to interacting systems. We are going to talk about fluids. We are going to talk about things like pair correlation functions. There, I'm just giving you a heads up of what's going to follow. That's Chandler chapter number 7 or something. We will be talking a lot about this function known as G of R, or the radial distribution function, which he's nodding his head. You're with Siddharth, are you? You're with Siddharth, right? So in his group, people calculate G of R a lot. So we will talk about, it's an interacting system. So anytime you observe a particle one place, it tells you something about the probability of finding a particle elsewhere. And we will develop machinery to calculate this. Once we do that, we will do something known as statistical mechanical perturbation theory, which is you have probably done some perturbation theory in quantum mechanics. This is going to be statistical mechanical perturbation theory, which was actually invented here. Well, it was invented by someone who used to be a professor here by the name of Zwanzig. He invented it in 1950s when he was a grad student at Caltech. And so it's known as Zwanzig statistical mechanics perturbation theory. You will see how that works. And then we are going to do a bit of phase transitions, look at renormalization group theory, and we'll finish all of this before 10th of May, don't worry, it'll work out. And what else did I want to say? But don't worry about all that. The next things that we are going to do again is electrons and photons. In photons, I have a story about photons that I want. What's the story? See if I can remember. Does anyone remember the name of Penzias and Wilson? No one remembers that name?
The basketball company?
Oh, come on, terrible. Not that Wilson. They won the Nobel Prize for something. They are the first people who discovered the cosmic background radiation. They were really able to figure out that the temperature of the early universe was around 3 Kelvin or something like that, or far out. And they had this big telescope. You should go and read up the story. They had this big telescope, and we will kind of show the equation that they had to use, which is this the Stefan Boltzmann I'll show you some extra material after I do photons as to how they could fit. Using the expression we derive in class basics, in one class, you can fit the Penzias, Wilson. So basically they had a big telescope and they were getting some noise, okay?
There were birds. Yeah. Birds.
There you go. You're talking about the birds?
Yeah.
Exactly. That's the experiment I'm talking about. They kept getting some noise and they're like, oh, what is this thing? And like these pigeons are taking a shit on the telescope. So they went around like cleaning all the bird shit and like shoving over the pigeons, and they still persisted. And that's when they saw that it had a signature in frequency. And that was the signature of the early universe. And we will derive an expression for that using StatMech. So you're all going to feel like, whoa, I'm so smart. Okay, that we will do in next 2 classes. So see you on Tuesday.